In this video, we're simply going to discuss chemical equilibrium, and we'll start with terminologies and formulas that are necessary. So this is simply going to give you an overview of everything that you need to know for you to be able to answer any particular question on chemical equilibrium. Now, if you're using Zumda or Raymond Chang, you've noticed that chemical equilibrium is demarcated into three parts. There is the first part, which is what we are doing in this video, chemical equilibrium, which is the test coverage. Then there's part 2, which deals with acidic and basic equilibrium. Then there's the last part, which talks about complex equilibrium. So there are three parts to this whole thing, and they are all connected. So this is just like the foundation that we're going to lay. So chemical equilibrium just deals with reactions where the rate of the forward reaction is equal to the rate of the reverse reaction. So we're just saying the forward reaction is happening at the same time. The forward reaction, I'll just say this, is happening at the same rate as the reverse reaction or the backward reaction. So if you are converting, let's say this is what you have, these are your reactants. We are trying to convert them into products. There's going to reach a point where the reactants and the products are going to remain constant. The concentrations are going to remain constant, meaning that the forward and the reverse reaction is now happening at the same time, because initially what you have are reactants. This is what you have. So reactants are given. This is what you're starting with, right? And we have 0 products. Products are here, right? They are 0. There's nothing at the beginning of a chemical reaction. So it starts properly as a forward reaction. The reactants are being used up, so they are decreasing, you notice. So as the reactants are decreasing, the products are being formed. These guys here are increasing. So you'll notice that there's a point where the reactants and the products will have equal amounts. They'll be constant. At that point, that's why equilibrium is established, and the whole system now will continuously move with it being at equilibrium. So a reaction does not start by being at equilibrium at the initial stage. It starts as a normal forward reaction. Then now, after a certain period of time, the amount of reactants is going to be the same as the amount of products. At that particular point, you're going to notice a good exchange between the two. So the forward reaction is happening and the reverse reaction is also happening. Yeah, so you need to take note of that. So now, if we have this type of reaction, we're just going to say there are properties you need to take note of. Yeah, so the properties is that at equilibrium, we say the reverse reaction is equal to the forward reaction. They're happening at the same time. Then B, the concentration of the products and the reactants will remain the same. So notice the key word that we're using. We don't say they are equal. We don't say they are equivalent. We just mean that it will remain the same. It will be standard. It will be kept constant. Whatsoever this guy is and whatsoever that the product becomes, they will be maintained from this point here. After they are almost equal, then they will be interchanging in between. Yeah. So depending on which side is going to be affected later on, we're going to be having what we call a left and a right shift. We're going to talk about that. But these are the two properties that we talk about here. Maybe I may add the third one, is that adding a catalyst does not affect the state of the equilibrium. So even if you add a catalyst, it won't change the equilibrium position. It won't shift. So neither the left side or the right side will be favored. So what I mean by left and right shift is, we're just saying, imagine you have nitrogen and hydrogen combining to give us ammonia. So let's take it as this achieving equilibrium. So this has already achieved equilibrium, and if I was to balance hydrogen, so nitrogen, I'll put a 3 there, so this equation is balanced, right? These are all in a gaseous state. This is in a gaseous state. Now imagine if the concentration here is 0.2 molarity, the concentration here is 0.3 molarity, then let's say 0.4 molarity. Let's say we have this. The equation here is balanced at equilibrium. After a certain period of time, imagine that we add concentration. So equilibrium, take it as if it's a seesaw. So take it as if it's like this. So equilibrium, we're just saying the reactants are equal to the what? The products. They remain constant. They remain the same, meaning it's balanced. Any change, any disturbance that you cause in the system is going to cause a shift. So that's called Le Chatelier's principle. Yeah, so Le Chatelier's principle. Probably too early for me to talk about it, but I need it for me to explain the right and the left shift. So we're saying whenever there's a change, whenever there's a disturbance in the system, whenever there is a disturbance in the system, in the equilibrium system, the system will shift. So we're saying the system will shift to consolidate the disadvantaged part. Or side, rather. So what we mean is this. Imagine this is a seesaw, right? These guys are balanced. So imagine here, I put what? I put 10. I'm going to use masses for you to understand this. Imagine here I put 10 kg, and this side here there's a 10 kg. So this is reactants and products. They're balanced on a seesaw. So now, if I was to change by adding, let's say I add a 2 this side, 2 kg. Meaning this is now what? This is now going to be a 12, right? So the system has been affected. The system is now imbalanced because now you are having 12 this side and you're having a 10 the other side. So when the disturbance is an addition on the content on the reactant side, so the disturbance we've caused is adding 2 kilograms, which is making the left side to have more than the right side. So how do we bring back this? The system will shift in a way that the forward reaction is going to be happening faster than the reverse reaction. So that we take 1 kg from here and put it the other side. Then the system will go back to equilibrium when this is 11 and that is what? 11. So that's what we mean by Le Chatelier's principle. Whenever there's a disturbance in the system, so we have to take into consideration the side which is being affected. And what is the effect? What are we doing to affect it? Are we adding or subtracting? Because what if instead of adding a 2, imagine if I deducted, instead of adding a 2, I subtracted 2 from this and this now became 8. Imagine if I say this is now 8. We have reduced the reactant side. So what happens? We are going to support the what? The left shift. So this is going to be what? We're going to the left, right? This is what we call the left shift. Because we're having the reverse reaction will be happening faster because 10 is more than 8. So we need to take 1 from 10 and give 8 so that it becomes 9 and they go back to being balanced by becoming 9 and 9. So that's what we mean by having a disturbance in the system. Okay, now we are here on the introduction. We're just saying the properties. Not affected, I may add here, not affected by a catalyst. So adding a catalyst does not affect a system. So a catalyst does not affect a system at equilibrium. These are the 3 most important properties of chemical equilibrium. Now, the other 2 things you need to know is that whenever you are given an equation, hoping that everyone is okay with balancing equations. So if a system is given at equilibrium, and we want to find out which side is being favored, whether the left or the right, or whether the forward reaction is happening faster. We get what we call the equilibrium constant, which is called Kc. Now, this is the equilibrium constant with respect to concentration. Then we also have what we call the equilibrium constant with respect to pressure. So this is just going to be products. So C to the power, the number balancing C here, that's the integer you put as a power there. That's the exponent. Then we put the product D and the number balancing it, we put it there. Then down, we simply put our A to the power A. Then we put our B to the power B. So this is if you are given concentration values. But if you are given pressure values, you still do the same. So meaning the pressure of C to the power C, the pressure of D to the power D, Then we have down here, we have the pressure of A to the power A and also the pressure of B to the power B. Now notice that we only use the Kp if you are given pressure values, meaning it's a homogeneous reaction. Homogeneous just means they're in the same state, and that will be in a gaseous state. Yeah. And also I must mention that when it comes to the Kc, we don't show solids in the Kc expression. The only things we can show in the Kc expressions are things in aqueous or things in a gas, as long as they have their concentration given in the question. Solids and liquids do not participate in forming, or rather making, the equation or the experiment to reach equilibrium. We do not indicate solids and liquids in our expressions, either the Kc or the Kp. And if you want to get, there's what we call delta N. We sum up the integers balancing the products, which is this small letter c and small letter d. When you add them up, minus the integers balancing the reactants, we can now relate the expression of, we know the expression of Kc and Kp. These guys are related. We just say Kp is equal to Kc, then RT to the power delta N. This is how these two equations are related. This is the relation between the two. And notice that Kc and Kp, so Kp and Kc have no units. These guys have no units. They don't have units. Though sometimes there is a special case where Kp sometimes is put in ATM. Sometimes they do indicate ATM, just to indicate that it's a constant with respect to pressure values. Yeah, but Kc doesn't have units. Then whether Kc or Kp, you should know that the value that you get, if Kc or Kp is greater than 1, meaning we're having the right shift. Then if this same expression is less than 1, meaning you're having a left shift. Then if it's equal to 0, meaning your system is at perfect equilibrium. So this means it's perfectly at equilibrium. That's what you have. So this is what we mean. In short, we're just implying that when you have more reactants and less products, you are going to have your K value. So whether Kc or Kp, I'm just going to say K is greater than 1 because you're going to have what? Your right shift. We're trying to balance them up to make them to be constant. Then if these are reactants, they are less as compared to products. Products are more, meaning you're going to have your left shift. K is less than 1. We're getting a what? A left shift. Hope this is okay. Hope this makes some sense. Then if I give you an expression, let's say I give you A converted to B, the K value is, let's say I give you K there, let's say K is equal to 2 for instance. If I flip this equation, the constant here was 2. If I flip it and I say B is equal to A, the constant here is going to be 1 over K, the reciprocal of what you had. So meaning the K for this reversed equation is just equal to 1 over 2. So you must take note of that. Then let me use the last 2 minutes to just explain what we mean by the IC table before we start looking at your tutorial sheet 6. Because what I'm giving you here is the knowledge that you need for us to answer any question on your tutorial sheet 6. So they are what we call IC tables. Now these are just easy to understand and read. This means equilibrium. When equilibrium has been established, this means the change that has happened. I just means the initial that you are given. So remember we said not all reactions start at equilibrium. They are going to have initial concentrations, right? Then equilibrium, there's a change that happens, then equilibrium is established. So we go like this. So in a chemical reaction, like I gave us here, let's say, I'll give you the same thing. Let's say, I'll use the same example I had given earlier on. We have hydrogen. This, let's say, equilibrium has been established. This is 3. This is what we're having. So initially, I gave you concentrations, let's say 0.2. Some people will use moles, it's okay. Then this is, let's say, 0.3 moles. So initially, there is no product at the beginning, unless the question says so. It's like you're starting to cook today, right? So you only have the ingredients. You want to cook nshima. You only have the ingredients, the milimew and everything else. You don't have nshima unless if kwenze chimbala. There was nshima that slept yesterday. Then that's what you're going to consider. Say, oh, I know I'm cooking. I need to consider what I left yesterday, so I just add on. So unless if the question says so, but we are always going to be assuming this to be what? To be 0. There is nothing at the beginning in terms of the product side. We only have the reactants. That's the I, initial. So like I said, some people will tell you to use moles. It's okay, but then it's just a waste of time, because at the end of the day, you'd have to convert all those moles back to concentration before you calculate your what? Your constant. The constant Kc and Kp cannot be gotten with the initial concentrations. We can only get them with the concentration at equilibrium. No wonder they're called equilibrium constants, because the concentration that we need is a concentration when equilibrium has been established. Hope that makes sense. So these are IC tables. The initial, they'll give you the initials from the question. Then they'll give you information that will lead to you finding the what? The change. But then I just want you to have an idea of what the table actually means. So when it comes to the change is going to negatively. So you let any letter, let's say X, be the change. We don't know the change, so we always take it to be negative with respect to the reactants. There's a change that is happening when you're cooking, right? There is a deduction on the milimew, because you're cooking. The reactants are not increasing, they're reducing. But your nshima is what? Increasing. So that change is going to be positive on the product side. Then everything is going to be affected with respect to the number in front. So here there's a 1. So meaning we need to put the change here is affecting nitrogen by a factor of 1. The change is affecting hydrogen by a factor of 3, because there are 3 of them. The change is going to affect ammonia by a factor of 3. So meaning at equilibrium now, at equilibrium we're just going to have this plus that. That's 0.2 minus the change. Then this is going to be 0.3 minus 3x. Then here we're going to have 3x. Now remember, I gave you a hint. I gave you a hint to say, in the previous question, I gave you to say ammonia, the concentration. Let's say the concentration of ammonia at equilibrium is 0.4, like the way I gave it to you. So you know what this is. It's just like simple math that you used to have in high school. So we know this is 0.4. So they'll say in the question, to say find the value of K, the equilibrium constant, if the initial concentration of ammonia is 0.2, the initial concentration of hydrogen is 0.3, and the concentration of ammonia at equilibrium is 0.4. So there should be a hint on how we should get the value of X. Something will be given to you. So this is what we are given. So we know to say 0 plus 3x was supposed to give us 0.4. So now we can use 3x to be equal to 0.4. We get the value of X. So that's a change. Once you get the value of X, 0.4 divided by 3, you get your answer. So once you get your answer 0.13 molarity, you replace it here. So we just say the actual values at equilibrium. So we just put your X. You know your X, so you can put it here. You get the value of this guy at equilibrium. You get your value here at equilibrium. Then you already have this one at equilibrium. You can now get your Kc. So your Kc is now going to be equal to, so let me just say your Kc, the expression first of all will be the ammonia, this to the power 2, then down you're having nitrogen to the power 1 and hydrogen to the power 3. So this is how you get your Kc. The concentration there is 0.4 squared. Then the concentration of nitrogen is 0.2 minus 0.13. That's going to be a 700. Yeah, so this is going to be, is this correct? Yeah, this is 0.07. So I don't have a calculator. Hope you're able to calculate this. Then the concentration at equilibrium for the hydrogen is 0.3 minus 3. X, we found it to be 0.13. So if we multiply this, that's going to give us 0.3 minus, this is going to give us a negative value, right? This is going to give us, okay, so for the sake of this example, just go along with this, but the answer can never be negative. Concentration can never be negative. So here I'm getting a 0.39, if I'm not mistaken. That's a negative 0.09. So I'll put it right here. That's negative 0.09. So you put it there, then you compute your answer. This will give you your constant. Then you check whether the constant is negative or it's less than. Is it less than or greater than 0? So it depends on what you get. Here we're going to get a negative, meaning Kc is what, less than 1, meaning what is going to happen? You're going to have what? A left shift. We're going to the left. The reverse reaction is happening more as compared to the right. So meaning this is a left shift. So hope you've gotten this, because this is basically what you need for you to be able to answer any particular question with regards to your test 1. So now we're going to go and we're going to look at your tutorial sheet 6 so that we see how we can apply this to just revise through. Let me explain everything that you need. And of course, there are other factors. So in case you are thinking to say, if an enzyme, a catalyst cannot affect the state of equilibrium, how about other conditions such as pressure, volume, and everything else? Can they actually affect the system? Yes, they can. So changes in the pressure, the volume, the concentration, they can lead to either having a forward reaction or a reverse reaction, depending on where the disturbance is being done. Are you affecting the whole equation on the product side or on the reactant side? So this is going to be explained properly by looking at this tutorial sheet. So this is your tutorial sheet 6. The first one, I'll just run through everything. The first one, they're saying chemical equilibrium is achieved when the rate of the forward reaction and the reverse reaction is equal. What are the two characteristics of the chemical equilibrium? So you see your answers here, the rate of the forward reaction and the rate of the reverse reaction. Then they are saying the concentration of the reactants and the products remain constant. They are not the same. We're not saying they are equal. Please get this right. When we say something is at equilibrium, we don't mean they are equal. We just mean they remain constant over a certain period of time, because the reverse and the forward reaction are happening simultaneously at the same time. Then here, number B, they're saying define heterogeneous. Heterogeneous just means the states are different. The states of matter are different, in which the reactant exists in two or more phases, meaning you have a solid, liquid, gas, those combinations. Homogeneous just means they're in the same state in a single phase. If they're liquids, everything is in liquid form. Gases, everything in a gaseous form. Yeah, so that's what you basically have. Then here they're simply saying state the relationship between equilibrium constant and Gibbs energy. So here we're just saying the relationship between Gibbs free energy and the equilibrium constant is basically given by the following formula. So Gibbs free energy is simply the same thing as work done. That's what we call it here in chemistry. We call it Gibbs free energy. So Gibbs free energy is equal to negative, the rate constant, the temperature, then ln, the equilibrium constant. This is basically the relation that they have. They are directly proportional to each other. Yeah, so the smaller the energy, that's when you have equilibrium being what? Being established. Because the meaning there is less collisions of particles. Yeah, so there is this. This is a formula you need to know, the relation between the two. Okay, so Gibbs free energy is simply related with the equilibrium constant by multiplying negative the universal gas constant and the temperature. The temperature has to be in kelvins. Then we have ln, the equilibrium constant. So the equilibrium constant has no units, meaning the units of the Gibbs free energy is going to be joules by the time you multiply the universal gas constant and your temperature, because the arrow that you're going to use here is 8.3145 joules per mole per Kelvin. That's basically what you're going to have. Then question 2 says write the expression for Kc for the following reactions. In each case, indicate whether the reaction is homogeneous or heterogeneous. So they are both. The first one here is homogeneous because you see that they're in a single state, right? This is gases throughout. Then the second one is a heterogeneous reaction because you have a gas, a solid, and a gas. So this is a mixture of two states of matter. And the Kc expression here should have been the concentration of the N2O to the power 1 the concentration of nitrogen dioxide to the power 1 over the concentration of the nitrogen monoxide to the power 3. That should have been the answer here. Then the same applies for number 2, but we remember we said in the Kc expression we don't show solids, so meaning the Kc is just supposed to be the carbon monoxide to the power 4 over, here we're going to put the nickel, everything here, the nickel carbon tetraoxide, this is CO, this is supposed to be everything here. Let me rewrite it. This is supposed to be the carbon monoxide to the power 4 over the Ni. Then you have carbon monoxide, 4 of them. This is to the power 1. And if you check, the equation is balanced because you have 4 of them, you have 1. So this is how it's supposed to be. This is to the power 1 there. That's what it's supposed to be. Yeah, so they had a problem with putting the answers here when they were typing them. So that's you seeing these guys here. So look at number 3. Number 3, they are saying when the following reactions come to equilibrium, state whether the equilibrium mixture of each reaction contains mostly reactants or products. So you look at the value of the Kc or the Kp. So the value here, this guy here, is less than 1 because of the power. You see that, right? So if the value of Kc is less than 1, it simply means that we're having the reverse reaction, right? So if we're having the reverse reaction, it simply means that we're supporting reactants, meaning we're going to have more reactants than products in this case where Kc is less than 1. Then here you are seeing Kp is greater than 1, meaning in a case where it's greater than 1, this is going to be a left shift, meaning reactants are more than products. Then here you're going to have products are more than reactants because we are supporting products. We're having a fast forward reaction, so products will be a lot as compared to the reactants. That's the answer there. Then your number 4, they are saying the decomposition of nitrogen dioxide at room temperature is shown. So nitrogen dioxide, so initially we have to write the equation. Nitrogen dioxide, when it decomposes, it's supposed to give off nitrogen and oxygen, right? This is what we're supposed to expect. Now we can put a 2 there, meaning we put a what? We put a 4 there. So is this true? No, we need to put a 2 here on oxygen. Sorry, this is going to be 2. We need to put a 2 there. These are all in a gaseous state. So the state, this is a homogeneous reaction. Then they're saying if the Kp value for this reaction at room temperature is at room temperature, so that's 25, right? So room temperature is 25. We take it to be 25 degrees Celsius, which is the same as what? 298 in kelvins, right? That's what you have. And we know the R value, we need to have 8.3145. That's what we have. We know the Kc and the Kp here. Yeah, so we're going to say the value that we need here is, we know how to get our delta N. Remember the relation between Kp and Kn, right? We said Kp and Kc, I mean. This is RT to the power delta N. So delta N is the sum of all the coefficients on the product side minus the coefficients on the reactant side. So here I have 1 plus 2, that's a 3, right? This 1 here and this 2 there, that's what is giving us the 3, minus this 2 here. That is what we're getting here. This is where the 1 is coming from. So in case you're wondering where this 1 is coming from, that's why they got this 1. Then now we can put our Kc. So our Kc is what? Is given to be 6.3 times 10 to the power negative 13 is equal to, we're looking for our K, our Kc, this is our Kp, we have 8.3, is it 8.3145 when there's no pressure mentioned. Then we multiply this by our temperature, so this is supposed to be 45 by our temperature, which is 298 to the power 1. So meaning we'll just divide by this. Okay, so here, just a minute. Okay, so here we're simply going to use the error value you're supposed to use here, guys, is point of correction. This has to be 0.08206. This is what you're supposed to use all the time whenever you're in need of the expression, the Kp is equal to Kc. So this is what you need to put. So this is supposed to be 0.08206. Then multiplying the temperature to the power 1. Then you divide both sides by 0.8206. Multiplying, they're saying for this reaction at room temperature. So we're taking room temperature to be that. So this, they were supposed to indicate the temperature there. There should have been a temperature value there. So this is 298. Yeah, we divide this side as well. It's 0.8206. Then times 298. Then we get your Kc. Yeah, that's basically what we need to get. And apart from that, the second question here, they are saying, calculate the standard free energy at 25, given the equilibrium constant is 1.3. So here we're using the same formula from giving you. Gibbs free energy is equal to negative RT. Then we are having ln, the constant. So for this particular equation, we use the R value to be 8.314, because the main reason why we take this to be 0.0820, this is because of the room temperature condition that we are choosing. Yeah, so we're choosing it to be something standard, which has a pressure value which needs us to use the R value, which is this guy there. So there are only two formulas that with different R values here, guys. So this is the first one. We're just saying Kp is equal to Kc, then RT to the power delta N. On this one, the R has to be 0.08206. Then on the Gibbs free energy formula, this one here, ln, the K value, the R value has to be 8.3145. That's what we're using there. So Gibbs free energy is what we are looking for. There's negative 8.3145. The temperature is 25, converted to kelvins, that's 298. Then ln is there on your calculator. Ln, the value you are given, open brackets, 1.3, 10 to the power 4. So let me just show you here. So if to change, there is here, where is that? Let me say, this is on your calculator, it's here. This is this, it looks like this. This is your ln. This is your ln option. So you can just say ln input, you say your 1.3, ln of 1.3 by 10, then you do to the power what? To the power 4. So this is equal to, then you punch, or then you say ln of whatsoever you got. Ln of this number is this. You're seeing it's 9 point that. Then we multiply it by the, so let me just cancel this a bit, times 298. You get this, 298 by 9.4. So let me just clear this. We see 9.4 times 298. Okay, so something like this. Then multiplied by your 8.3145. Okay, you get something like this. This is what they've gotten here. So this is your negative. So just put it here. That's 2 point, you can say 23. So you can just say this is the same as negative 23.4. This is kilojoules. You can put it like that in kilograms. Yeah, so that's your number 5. Then your number 6, they're saying the following equilibrium was attained at this temperature. Calculate the Kp when Kc is given. So Kp is what we are looking for. Kc is given as 67. Then we know that the R you need to use here is 0.8206. The temperature is 823. The delta N is simply, there's a 1, there's a 2. Then even this side there's a 1, there's a 2. So meaning 2 minus 2, that's simply going to give us a 0. So meaning this whole thing here is a 1, meaning Kc is equal to Kp, which is just what? 67. Hope this is okay. Then look at number 7. Number 7, they are saying ethylene and water react under appropriate conditions to give ethanol. The reaction is given as follows. This is what we have at equilibrium. So they needed to give us the formula here. Let me just rewrite it for us. So the original equation has to be ethylene, which is C2. Then you have H4. This reacts with water to give us, so they go at equilibrium. It gives us C2. Then this will give us H5, then OH. This is what you get. So now if we try to balance this equation, we'll see that the hydrogens are okay. There are 6 carbons, there are 2 oxygen, there's 1. So this equation is self-balanced. Then they've given us the concentration at equilibrium to be 0.0148. Then for the water, it's 0.0336. Then for the ethanol is 0.180. So these are values at equilibrium. So they've already said at equilibrium, meaning our Kc is going to be the alcohol. The expression is just going to give us the alcohol, the ethanol, to the power 1, right? Then over the ethylene, which is this 4 to the power 1. Then we have the water, which is to the power 1 as well. So we just do the replacement. Put this, put that, put that. This is what they have given us here. That's how they got this answer there. So hope this is okay. That was your number 7. It's just direct. So you need to be careful with the question. If they say it's already at equilibrium, meaning we're going direct. But question number 8, this is now where we need to use the IC table. This is the best question that you can use to understand the IC table. So let me just put it here. So they're saying a mixture of 0.1 mole of nitrogen monoxide and 0.05 mole of hydrogen, and you're having 0.1 of water, is placed in a 1 liter vessel. So 1 liter just means that's the total volume. We can divide this by 1 liter. So you can rewrite these as concentrations, because divide each one of them by the volume, you will still get the same values, right? So we're just saying this is molarity. I'll use capital letter M here. Where are these molarities coming from? The molarities are coming from dividing each number of mole by the total volume. So that's how we're getting these guys here. So initially, this is your initial, right? Your I. These are what are given in the question. So hope this is okay. We just write what we've been given. Nitrogen, nothing was given. So we're assuming it to be what? To be 0. Only water. So water, there was some leftover water somewhere. No wonder we're having water starting with something there. Then they're telling us that at equilibrium, the nitrogen monoxide became 0.062. So we're putting negative 2x, plus 1x. These are the changes that are happening there. Then we're going to have, let me probably rewrite this. Okay, so we're having nitrogen monoxide given there. Then we're having nitrogen given on the other side. These are all in a gaseous state. This is what you are given. Even water is in a gaseous state. So now they gave us the initial number of moles. So the initial number of moles for nitrogen monoxide was 0.1 divided by 1 liter to get the concentration. That's where the 0.1 molarity is coming from. The hydrogen is also the same. It's going to be 0.05 molarity. Nitrogen, we are not given water. We are given, and it's simply 0.1. This is 0.1 as well. So this is what we are having. Now we know there's going to be a change. The change, let's call the change to be x. It will affect this by a factor of 2 because there's a 2 in front. That's what we said on the IC table. Yeah, so we're having a negative 2x. Then here it's going to be negative 2x. Here we're just going to be put a positive 1. This is a positive 2x. Then at equilibrium, the only thing we are told is that at equilibrium nitrogen monoxide, on the question they say nitrogen monoxide, at equilibrium it's 0.062. So meaning nitrogen monoxide, this is 0.062. There is nothing else that has been given to us. So we're going to use this first column here to say 0.1 minus 2x should have given us 0.062. So we're using this to get our x. So we're going to have negative 2x is equal to 0.062 minus 0.1. Then we divide this side by negative 2. We divide by negative 2. So x is equal to 0.062 minus 0.1 over negative 2. And when you punch this on your calculator, this should give you something like x is equal to This is giving us 0.019 molarity. That's what we are getting. Now that you know your value of X, we're simply going to put our X here. You put your X there. So meaning this minus 2 times the answer that we've gotten, it will give you for hydrogen here. Let me just use a different color. So for nitrogen here is simply going to be the same thing, which is 0.019, right? Because it's just X. This part here, you're subtracting. So that's for hydrogen. So hydrogen is going to end up giving us 0.012. Then for water, we're adding. So for water, since we're adding, this is going to be 0.138. So these are the concentrations at equilibrium that we can use to get our equilibrium constant. So now we come here, we just write the expression. Let me just erase this to write the expression there. So the expression for Kc is going to be water. So the water, the concentration is 0.138 raised to the power what? 2, because there's a 2, multiplying the nitrogen 0.019 to the power 1, then over the nitrogen monoxide, which is just 0.062 with a 2 there. Then you have the hydrogen, which is 0.012 again to the power 2. Yeah, so when you punch the top part and punch the bottom part, the total answer there for the Kc has to be 653. That's what they got. Then 68. It has no units, so meaning we just leave it to be the way it is. So that's what happened on number 8. That's what was done. So the same thing would be done for number 9. So you can try to pause it first, then try to compute this. Yeah, so this I'll leave it to you as a task because it's the same thing. Except here, we are looking for the value of X because the Kc has been given, right? So the same thing, we get the concentrations. They're telling us that the initial concentration is that, meaning we just have the initial concentration of the reactant. So meaning the products, we're going to assume zeros. That's what you are seeing there. The equation is balanced. So the change is going to be negative 1x, positive 1x, positive 1x. So this is what we are having at equilibrium. We're going to create a quadratic equation that tells us that the Kc is equal to x times x. That's simply x and x over 0.002 minus x. That's what you get. So now we're just going to create something that looks like this. So let me just explain this in terms of the assumption that they did. So on number 9, hope you're okay on how we are landing on the expression for Kc and also the IC table. Hope you're okay with that. If you don't find it okay, please try to reach out. Maybe I can give you something that can help you understand it. Then we're saying Kc should give us this X, the concentrations at equilibrium. In the table here, in the diagram, you are seeing I'm focusing on this. This is what I'm getting. The products, it's x times x. That's where the x squared is coming from. Over this number this side. So that's what we are having. Now, the Kc expression is so small such that we can ignore. This is 2 point. This is the down part is simply 0.0002 minus x. The Kc we know, we're told there it's 2.19 times 10 to the power negative that is equal to x squared over 0.002 minus x. So we're going to carry out an assumption. Assume that 0.002 minus x is the same as 0.002. So whenever the Kc value is very small, this is less than 1 but greater than 0, right? It's very, very small. It's almost like a 0 because this is going to be 0. We have over 16 zeros before we come to having 2119. So we're saying it's very small, meaning the reaction was simply having a reverse. It was supporting reactants, meaning the reactants rarely dissociated. So we can take the assumption that the change in the concentration of the reactant is negligible, so that this here is going to be 2.19 times 10 to the power negative 18 is equal to x squared over 0.002. There's a 0 there. We can cross multiply, meaning x squared is equal to 0.0002, then multiplying 2.19 10 to the power negative 18. So maybe to explain this further is like it's like when you give a baby, a 2-year-old baby, an apple, right? If you give a baby your apple, then they take small bites. You can't complain that your apple has been eaten. It's almost as if the bites are negligible. You can actually confidently say, I still have my full apple because the change is negligible. It's very tiny, almost insignificant, right? That's the reason why we're doing this assumption. Then here we can square root. So x is equal to, when you multiply this and square root, that's the change that we're going to get to be, so the change is simply giving us a 6.62 times 10 to the power negative 7. Once you get the change, you can now find the equilibrium concentrations of everything that you need, because the equilibrium concentration of this guy is x, which is the same 6 that we've gotten, this guy here. The same applies there. Then this is minus that. You notice it's almost going to be the same. Look at what happens for the change. Yeah, this is the same as, almost the same as the original number, which is 0.002. Yeah, so hope this is okay. This here was supposed to be just 2 zeros. Yeah, this is 2 zeros. So it was 0.002 minus x. Assumed it to be 0.002. Yeah. So that's what you have there on question number 9. So number 10, it's almost the same. Hope by now you are confident enough to even attempt this. So the first one, so the equation here was supposed to be given. So they're saying what sufficient, this was given. Okay, so this, I'll just leave it to you, because once you get the correct equation, this is similar to question number 10. You get the concentrations there, making sure that you divide each of these by your total volume. They're saying the vessel whose volume is 2.5, so you can just divide the number of moles of everything by the total volume to put the concentrations there. Then you continue in a similar way. Yeah, so this is okay. You can check that out. If you have challenges in coming up with the equation, you can just reach out on my number. I've put it there. It's somewhere there on top. Okay, yeah, so this is the same thing. I want something new. So here you have considered the following equilibrium for which the enthalpy is less than 0. So if it's less than 0, meaning it's negative, meaning the reaction is what? Exothermic. So if a reaction is exothermic, so here we needed the equation. We need to know what we're dealing with, because we cannot guess. How will each of the following changes affect an equilibrium mixture of the three gases if oxygen is added to the system? So let's take this to be oxygen, because here I completely don't know what was here. Yeah, even okay. So I think it's my laptop that's showing this, because here there's actually a normal. So according to I thought it's the paper, but it's actually how the document was opened. So this is supposed to be 2s2 then plus oxygen. This is giving us something like 2SO3. So this is the equation. So even here at first here, guys, yeah, so the equation, this is actually proper in the document. There is SB2S3 then plus, this is 3 hydrogens atoms to give us, we're having 2Sb then plus 3 hydrogen sulfide. This is what you're getting. So just a hint here, they're saying a vessel whose volume is this was filled with 0.1 of antimony sulfide. This is the first guy. So meaning use this, divide this by, you divide 0.01 divided by the 2.5, that will be the answer here. So here it's 0.01, the moles that you have, divided by 2.5. That will be, this is in moles, Yeah, this will be in liters. So divide it to get the concentration there. Hope that's okay. After the mixture came to equilibrium in a closed this, the gaseous this was removed, the hydrogen was dissolved sufficient, added this, blah, blah, blah. Then they're saying 1.029 of lead was obtained. What is the value of? So lead, this is supposed to be, was obtained. What is the value of the Kc? So this is supposed to be Sb. This is supposed to be just Sb, not lead, but rather Sb. This is what? Lead sulfate, right? Okay, lead sulfate, hydrogen sulfide. Okay, so this is what we are having. The change here will be, the equation is balanced, so this is going to be negative x. Yeah, then this is going to be plus 2x. Also, this lead sulfate, sufficient lead was added to react complete with the hydrogen sulfide. So here there are two questions in one. The first thing you need to do is to get the change. So if you get the change is gotten to be, okay, so the x value we're supposed to get at the end of the day is this guy here. Then once you get the change will help you to get the equilibrium concentration of hydrogen sulfide. Yeah, this guy here. Once you get the value here, you react this with the lead, you do your comparison, more to more ratio comparison, then you find, they're asking for the Kc. So we just go direct, we use this. Yeah, there's no need of anything else complicated, so we just go direct. Yeah, hope that's okay. Please reach out in case this thing is actually confusing, because I'm taking it, I don't want to waste time, so that I just tackle everything to give you hints on everything. So look at number 11, they're saying oxygen added. When you add oxygen this side, meaning you're increasing the reactant side, so you're going to have a right shift. Yeah, so we're going to have a right shift. Then the reaction mixture is heated. This thing is trying to get rid of heat, so if you're heating it, you're slowing it down, so you're going to have the reverse reaction. They said the enthalpy, this means energy, heat. So heat is negative, meaning this is exothermic. Then when you're adding heat, you're slowing it down, so we're going to have a left shift. Then a catalyst, meaning nothing happens. We remember we said there is no change that is going to happen when you add a catalyst. Then the sulfur trioxide is removed, so sulfur trioxide is here. When you remove this, meaning you're reducing it, so you're going to have what? Forward reaction. Yeah, so a forward reaction, which will just be a right hand side. Then number 12, I wanted to talk about this part here. Yeah, so number 12 has to do with what we call the solubility product. So when they give us something, so I'll explain number 12 up to 14 on a different slide, since I have the question here. So there's what you call KSP. This is called a solubility product. So what we mean by solubility product is when a metal ion or something that was in an ionic bonding dissociates. For example, if I give us something like sodium chloride, let's say sodium chloride, it dissociates completely. So things in ionic conditions, or rather ionic bonding, can also establish equilibrium, but we're just interested to the extent at which they are going to dissociate. So when this guy dissociates, it's simply going to give us the chlorine and the sodium ion. KSP is simply the concentration of the ions that have dissociated, multiply them. So this is what we are getting. So if it was aluminium, let's say I give you aluminium chloride, like this guy dissociates, gives you aluminium 3+, then chlorine negative with a 3, because there were 3 chlorines this side, right? Your KSP expression will just be the concentration of aluminium. There's a 1, so I'll put a 1. There's a 1 in front. Then we are saying this here, we put a 3 there. This is how we get the KSP. So the solubility product is the constant we get. When they say solubility, they mean the concentration of something. So like question number 12 there, they're simply saying, write the KSP expression for calcium fluoride. So calcium fluoride with a 2, this guy dissociates to give us calcium 2+, Then you have fluorine negative with a 2 in front. So meaning the expression is just the concentration of calcium to the power 1, the concentration of fluorine to the power 2. This is the expression. That's the answer that they've written there. That's where it's coming from. Then the next one, so that's what they have written there. The next one, they're saying copper 1 chloride has the KSP value of this. Calculate the molar solubility of copper chloride in what? In pure water. Right? So the constant has been given. That's what we have. So now if we're trying to calculate the whole thing, we're simply going to get, so this is question number 13. They're saying copper chloride. So this guy dissociates to give us copper 1, and chlorine is also negative. So the KSP was supposed to be the copper plus and the chlorine negative. So the constant KSP was given there. It's 1.9 times 10 to the power negative 7. Then this is equal to, we don't know here. Yeah, so we don't know. So if we have x here, meaning here there will be the 1 times x, that's going to be x, 1 times x, that's going to be x. So I mean this is just x, and that's x. So that's the x squared, which is equal to 1.9 times 10 to the power negative that. So we can square root, meaning the concentration here is going to give us the square root there, which is a 4.36, then times 10 to the power negative that. Meaning the solubility, the molar solubility of copper and chlorine are both this. So copper plus is the 4.36, 10 to the power that molarity. The same applies for the chlorine. So this is the molar solubility of these two, the level at which they are going to dissociate. Yeah, so take note of what I had done earlier on. We just say, if you know the concentration of the first thing, so like here, this is 3 chlorine negative. If here it's 2 molarity, if that's the concentration, you multiply, there's a 1 there, right? 1 times this, more ratio. This is going to be 2 molarity. Then 3 times that, that's going to give us a 6 molarity. Then you can use these two, you get your what? Your KSP. KSP will just be 2 to the power 1 and 6 to the power 3. Yeah, you get this. So that's what we basically mean. Then how about the last one? The last question, they are saying calculate the molar solubility. That's number 14. Calculate the molar solubility of silver chloride at this, in that condition. The KSP for that has been given. Okay, so on the last one, or number 14, they're saying calculate the molar solubility of silver chromate at this, given that in 0. this, the KSP for that is given to be that. So we have two mixtures here. We're having two solutions. So I'll write both solutions. So I'll write the first one. The first one is, there's Ag2, then there's CrO4. So here we're given, they were telling us this in, there's 0.2 molarity of the silver. So this is the silver there, nitrate, that's what we're having. Then the KSP, so this is what we are having here. So this is what we call a common ion effect. So common ion effect just means we have something common between the two reactions that we have. The only data that we are given is the information pertaining this guy here. We know the information about this silver nitrate, so we can break down this part here. When we break it down, so we have two equations. Equation 1 is going to be this Ag2, the chromite, this guy here. When it dissociates, it gives us Ag, this is positive, plus the chromite here, which is 2 negative. So meaning this is going to be, you put a 2 there to balance it. The second equation is the Ag, this guy here. This simply dissociates to give us Ag plus. Then you have this guy here. Now the common ion, what we mean by the common ion effect is you're seeing something common between these two, right? And the concentration here was 0.2 molarity. So meaning even here it's going to be 0.2, and also here it's 0.2, right? That's what we're having. But we're just interested in this because the whole question is based on this guy. That's what the question wants. We're interested in the first thing. Yeah, the second thing is just like supplementing, help us to have a starting point. So this is what we need. But we have something here which was donating 0.2 ions of silver. So when we get our equation there, so our equation that we're going to use is to establish an IC table is the Ag2CR4. This equilibrium has been established. We write 2 Ag plus, then we put the CR42 negative. The initial concentration that we have is just 0.2. That's the only thing that we have in the question, because it came from the common ion thing that we had. Now, we don't know what this is, but the change and the guy at equilibrium, we know to say here the change is supposed to be positive with a 2. Then here we know the change has to be, so here we put a 0. The change here has to be positive x. We know to say this has to be 0.2, then plus 2x. Then here we're having x. They gave us the KSP, so we know what KSP is. KSP is supposed to be the Ag to the power 2 and the CR2, or this is a 4, negative 2. This has a 1. So the KSP is given to be 1.2 according to the question. So we're having 1.2 times 10 to the power negative 12. Here we have 0.2, then plus 2x to the power 2. Then here we're just having x to the power 1, right? So we're just solving for x. This is going to be a whole quadratic. Though we can do our assumption again. Our assumption can still be 0.2 plus 2x is approximately the same, to avoid the quadratic. But if you want, you can expand this and solve for x. It will be a quadratic to get two answers. The two answers, one will be positive, one will be negative, meaning you get the positive one. Then if they're both positive, you get the smaller one. Yeah, so this is going to be the same as that. So now we are solving 1.2 times 10 to the power negative 12 is equal to 0.2 to the power 2. Then there's an x here, so now we can just get this to the power 2. Then you have 0.2 to the power 2. We get our value of x. Our value of x is simply going to be 3.0 times 10 to the power negative 11. So if you get this, the question was asking for the molar solubility of Ag2, that, so meaning this is going to be the same thing, because they're in a ratio of what? If you come here, they're in a ratio of 1 to 1, right? If x here is this number we're from getting, 10 to the power negative 11, this is 1, so multiply this by 1, so this is 3 times 10 to the power negative 11. So that's how they got this final answer here. So hope you're able to follow. This assumption is always necessary to avoid using a quadratic. Yeah, so that's basically what you need. Yeah, so this marks the end of equilibrium.